Yes. So good evening, everyone. Welcome to the third session of problem solving for the course Structural Analysis 1. So before we go ahead, I think there's a question in the forum, discussion forum, about the recorded videos of the problem solving session. So the person has requested for the Excel sheet containing the links to the videos, but I'm not sure if we are authorized to share it. Instead, let me share the YouTube link of my sessions. So from there you can access mine. Probably the other TAs will also be responding very soon. So let me share this. So the playlist. Yeah. So let me share this playlist link. If okay, I hope that is you would have received it. So let's get started with today's section. So what are deflections? So as you will all be already aware of, so deflections are so deflection is basically some kind of deformation. So when very slender members when we have very slender members that undergo deformation, You know, as you are all aware of the assumptions in the beam theory, the cross sections do not deform much. If you take a section, the section before deformation and the section after deformation, there is not much difference. It rotates rigidly, but the maximum deformation occurs in the lateral direction along the center line. So if you take 2 points, so if you take a point on the center line before deformation, it would have shifted laterally by some distance. So this is what we call as deflection. So when a very slender member undergoes deformation, the center lines, the points on the center line move laterally, displace laterally. So that displacement, we call it as deflection. Then, so the other thing that we need to know is elastic curve. So what is an elastic curve of a beam? So this is also simple. If you pass a curve, so you connect, so it's a curve connecting the centroids of all the sections. In the beam, in the deformed beam. So we have a beam like this. You have some boundary conditions. You apply certain loads. It deforms. So this is the deformed beam. In the deformed beam, if you connect all the points along its, so this is a section, this is another section, this is another section, this is another section, this is a section. So take all these sections, find their center points, which is called the centroid. A curve passing through all the centroids in the deformed beam, we call that curve as the elastic curve. So what it has, so if you subtract the vertical position of a point on the elastic curve from the original position, what you get will be the deflection. So this part of the course is all about finding deflections for beams, statically determinate beams. So we'll be going through two methods. One is double integration method. One is the double integration method, and the second one is moment area theorems. There's also a third method and a fourth method, which will come up in the next session. The third method is, conjugate beam method, which is a very powerful method. And we have this, as we did for trusses, we have the unit load method. So today we'll be looking at these two methods for solving problems in beams, statically determinate beams. So let's go ahead. So double integration method. We'll start with the double integration method. So as you all know, you can recollect from your strength of materials. How do you start the beam theory? You consider a small section of the beam. So you take a section like this of very small length, and you see how it deforms, right? You are under an applied moment, it deforms like like this. So you extend the faces all the way up. Meets at a point, and this is the beam center line. You call this distance as the radius of the curvature rho, and the beam section has a moment of inertia I, and it is made up of a material E with Young's modulus E. So you know, based on all these assumptions that plane sections remain plane, they remain normal to the neutral axis and so on, what you get the bending formula, which is 1 by rho is equal to m by EI. This holds under pure bending. What is pure bending? The beam is just subjected to a bending moment on everywhere at all sections. It doesn't have any shear force or axial force. So under these conditions, the beam is linearly elastic, small deformations, pure bending, we have this formula between the radius of curvature rho and the bending moment m. Now, if you take the elastic curve, right? So this is for the case of pure bending, but in general, if you take the elastic curve, it may be a curve like this. So if you take a point on the elastic curve, it has a curvature. So associated with that, you have a radius of curvature. And from basic calculus, you know that the radius of curvature of a smooth curve, right? If you have a smooth curve defined by y is equal to f of x, from basic calculus, you know that the radius of curvature rho is given as, or in fact, the curvature, which is the inverse of radius of curvature, is given as d square y by dx square divided by 1 plus dy by dx, the whole square, the entire thing, power 3 by 2. So in linear elasticity, under small deformations and small rotations, we assume that dy by dx is very much small compared to 1. So what is dy by dx? Dy by dx is a kind of rotation that is very small compared to 1 radians. With this assumption, if dy by dx itself is very small compared to 1, then dy by dx the whole square will be much smaller. So the denominator can be roughly approximated as 1. So what do you get? You get the curvature of the beam at a given point as d square elastic curve. So if the beam is initially straight, as I said, if the beam is initially straight, so this is the center line of the undeformed beam, and you have the elastic curve, which is the center line of the deformed beam. The difference is what is the deflection. So if you take the x-axis initially to coincide with the beam, then the vertical deflection is equal to the coordinate of the elastic curve. So let's just call the vertical deflection b. So the radius of curvature is related to the deflection as d square v by dx square, approximately, once you ignore this term. But from pure bending, what do we have? We have that this relation between the moment and the radius of curvature at a point. So comparing this with this, at a given point on the elastic curve, we have this relation that d square v by dx square is equal to m by ei, where m can be a function of x and ei also can be functions of x in general. So this is the basis for the double integration method. So Yeah, but what is important in this is the sign conventions. So the sign conventions are very important. So sign conventions. So first, the deflection V measured upwards is positive. Second thing, so if this is positive, so what we say, if you have a curve and your origin is here, so measured upwards is positive. This V is positive. If it's measured downwards, it's negative. So if this is positive, then dV by dx, which is this angle. So tan of this angle is dV by dx. So that is positive if it is measured clockwise. Sorry, counterclockwise. So dV by dx or the rotation or the slope is positive when measured counterclockwise. The third thing, moments. So the way we have denoted it, right? Sagging moment. Sagging moment. Sorry. Sagging moment is positive. So there's also the other counterpart. So if deflection is downwards, it is negative. If you have clockwise rotation, it's negative. And if you have hogging moments, it's negative. So this is clear. Now, what is the procedure? Let's look at the procedure to use this method. So as usual, procedure. So first step, right? So always the first step, you can right away start with the integration. You can get the moment and start with the integration. But it's always a good idea to sketch the elastic curve. Even before you have solved for it, based on your intuition, it's always a good idea to sketch the elastic curve. Then you will be given the loads and the boundary conditions. So solve for the bending moments. So first solve for the support reactions in a statically determinate structure. So once you get the support reaction, get the bending moment. As a function of the beam coordinate x. So this means you need to set up a local coordinate system on the beam, a Cartesian coordinate system on the beam. We'll get to it when we solve the problems, you will know. Then, so then use the relationship, right? So we have d square v by dx square is equal to m of x by di of x in general. So I integrate it twice. Integrate it twice. Integrate it twice. So you'll get dv by dx is equal to integral. So it's a indefinite integral m of x by ei dx plus an unknown constant c1 and integrate it again. So v of x will be m of x dx by ei. So the entire thing integrated again with respect to x plus c1x plus c2. Now we have the unknown constants which you have to determine using boundary conditions. So you'll have boundary conditions. And in some cases, you will also have continuity conditions. So these will help you determine the constants C1 and C2. So once you got that, that's all. You have completely determined the deflection profile V of x. So then you have to apply the sign conventions to determine if it is upwards or downwards. So is that okay? Any doubts? Okay, let me also discuss the next method, then we'll get to it. So the other method is moment area theorems. So we just saw that dv by dx, or rather d square v by dx square is equal to m of x by ei. Let us call the slope dv by dx as theta. So dv by dx is in reality tan theta, but if we consider very small deformations, very small deflections, dv by dx is very small. So theta is approximately equal to tan theta, approximately equal to sin theta, and so on. So what is d square v by dx square? We get this d theta by dx is m of x by ei. Now let us integrate this equation between 2 points. Okay. So if we integrate this equation between 2 points A and B, so if you have a elastic curve, you have a point A and you have a point B at this point, and you're integrating this governing equation between these 2 points. So when you integrate between these 2 points, at this point you have a tangent at an angle theta A. At this point you have a tangent at an angle theta B. So this will be theta A. This will be theta B. And how are they related? So integrate this, you get d theta by d. From the point A to B, you get theta B minus theta A is equal to integral m by ei dx from the point A to the point B. So this quantity, we can represent it as theta B with respect to A. That is the change in the slope of the tangent to the elastic curve at the point A, point B with respect to the tangent at the point A. So that is this quantity. So this forms the first theorem. So the first moment area theorem states that, and what is on the right hand side? So this is nothing but the area under the m by ei curve from point A to point B. So this is clear. So what is the first theorem? So the first theorem states that the change in slope between two points A and B on the elastic curve equals the area under the M by EI diagram between these 2 points. That's all. So it follows the usual notation. So if we have a positive sign for the area, so if you have a positive area, it means the change in the angle is counterclockwise. And if you have a negative area, it means the change in the angle from A to B is clockwise. So this is simple. Now let's look at the next theorem, right? So the elastic curve is something like this. And you have the point A and the point B. So with respect, so if you want to determine, and let us draw the tangent at point B. So tangent at point B is something like this. And A lies here. So if you consider a small segment of the curve like this, a very small segment of the curve of length dx. So since the angles are small, dx will be approximately equal to the curve length. Over this length, the tangent changes by here, say it is θ1, and here it is θ1 plus d theta. So what is the length of, so this is a very small distance. So at a point x, right? So at a point x, what will be the length sweep by the tangent? So as the tangent rotates, it will sweep about this point. So x is of course much greater than dx. It will sweep an angle d theta, and corresponding to that, the deviation is x d theta. So, but what is d theta? We already saw that d theta by dx is m by a. So d theta is m dx by dI. So the deviation at a given point due to a small segment of the curve is x d theta. So let us call this deviation dt, tangential deviation. So this is m x dx by dA. So m is also a function of x, remember that. So finally, if you take 2 points, so if you take a point here, how much it totally deviates with respect to a tangent drawn somewhere else is integral of all such small segments. So t of a point A, the vertical deviation of a point on the elastic curve with respect to the tangent drawn somewhere else. This distance. So if you have something like this deviation is called t of A with respect to B. That distance is equal to integral dt from the point A to B, nothing but integral A to B x m of x dx by dI. So this is the second moment area theorem. So what is it? The vertical. The vertical deviation of a point, let us call the point A, on the elastic curve with respect to a tangent drawn at a point B on the elastic curve equals, so what is it? We say T of A with respect to B is equal to integral A to B x m of x dx. And this quantity, as you can see, is the moment. So if you take the moment of the area below the m of x, so this is the position and this is the kind of some area quantity. So it is the moment of the, so it equals the moment of the area under the m by ei diagram between the 2 points. Most importantly, about the moment should always be taken about the point A. Wherever you want to find the deviation about the point A. So that's important. So this is the second theorem. So these two, but you should be careful that this theorem by itself. So note this theorem doesn't give deflections. It gives a tangential deviation. That is, if you have a beam, right, a real beam, under some loads, and this is the deflected profile. So if suppose this is point A and the midpoint is B and this is point C. So if you have to compute this deflection, this is delta, you can't get it directly from this theorem. So if you say point, what is TA A with respect to B? It means you draw a tangent at the point B. With respect to this tangent, what is the position of the point A? So this quantity is T of A with respect to B. So, and what is T of B with respect to A? Both are not the same. So again, the same beam. You draw a tangent. So this is, we want to see what is T of B with respect to A, right? So you draw a tangent at A. This is the point A. This is the point B. And this is the point C. So with respect to the tangent drawn at A, what is the vertical displacement of the point B? So this is T of B with respect to A. So you should be very careful. T of A with respect to B and B with respect to A, they are not same. And they don't directly give the deflection in any case. So what is the procedure? So procedure. So as usual, the first step, support reactions and bending moment. And the second step is you have to choose the points correctly. So we'll see how to do it. Choose the points to compute T of B with respect to A or A with respect to B. The reason is it doesn't directly give the deflection. It always helps if we use a support, right? Because we know at the support the displacement is 0. So using that, you may have to use the theorem again. And then once you have done it, just use the moment area theorem. So just to demonstrate this, let me solve this, then I'll pause for questions. Okay, so this is a given problem. We have this point C. Let us call this point as A and this is as B. So it's a simply supported beam subjected to an end moment of 5 kilonewton meters and it's of total length 24 meters. So as usual, what is the first step? So step 1 is to determine the support reactions. So let us take moments about the point A. What are they? Minus 5 kilonewton meters plus RB, reaction at B in the y direction, into 24 meters is equal to 0. So we get the reaction at B as 5 by 24 kilonewtons. Now, so what will be the reaction at A? Just use vertical equilibrium. There are no vertical forces, so it should be equal and opposite. It will be minus 5 by 24 kilonewtons. Now, that is okay. So once we have got this, let us find the bending moment diagram. So what is the moment at the point A? So moment at the point A is 5 and it is sagging moment. So it is positive. Here it is 5 kilonewton meters. At this point, it should be 0. We can also check if it is really 0. How? So it's so what is, just take moments about this point. We have a support reaction of minus 5 by 24 acting at 24 meters. So the moment due to that force will be minus 5 and the applied moment itself is 5. So the total moment at the point B is 0. So it is. So this is the bending moment diagram. Now given this, what is the moment by EI diagram? It is nothing, it's the same. So the M by EI diagram is the M by EI diagram is the same. So the maximum will be 5 by EI and this is 0. And the total length is 24 meters and the point, this is the midpoint. So this is at 12 meters. This is the point C, this is the point A, and this is the point B. So as I always said, if always sketch the elastic curve, right? So let us sketch the elastic curve, what it looks like. So let me denote the initial configuration in dotted lines, undeformed configuration dotted lines, and there's a moment acting like this. So what it does, it tries to rotate the beam. So beam will rotate like this. And they say there's no load. So this will be the initial configuration. The maximum the deflection will occur somewhere towards the left because the moment is acting here. It's not symmetric, right? Now, the question is to find out what is the displacement of a point C which is located midway. So how do we find it? So this is the displacement of a point C. Let us call it delta C. Okay, now how do we get delta C? All that we have with the moment relations, right? All that we have with the moment area theorems are relative. They don't give absolute displacements. They will give the difference in the tangents and so on. So let us do this trick. Let us draw a tangent at the point A. So let this angle be theta A. So we are drawing a tangent at A and the angle is theta A. And what do we know? We know that the displacement of the point B is 0 and the displacement of the point A is 0 because they are supported. Slope at the point A and slope at the point B are unknown. But can we get it? So, and what is this quantity? So this quantity will be the deviation of the point C with respect to the tangent drawn at the point A. Similarly, what is this quantity? The deviation of the point B with respect to the tangent drawn at A. Now I hope you have got the trick. So what is the relation between TCA and TBA? Yes? Yes, I hope I'm audible. Is that okay?
Yes, sir.
Yeah, so is there a guess? Could you find a relationship between TCA and TBA? All the lengths are given. Sorry, I couldn't hear you.
Similar triangle.
Yes, very
Similar
good. It
triangles
is,
we can.
yes. So using similar triangles, you can say TCA by TBA is AC by AB. So it is halfway, so it is 1 by 2. So we got that TBA is equal to 2 times TCA. And what is delta C? Sorry, it's not TCA, right? TCA is only so much, but we should see the full height. So it is
TCA plus delta C, sir. TCA
delta C.
plus delta
Yes.
C.
Yes. So it is 2 times TCA plus delta C. Now using this, you will, so TBA can be directly computed and you can get TCA also can be directly computed. So what is that you need? Delta C. So it is, so delta C is equal to TBA by 2 minus TCA. So that's all. So let us just directly use the moment area theorem. So what does it say? Now what is TCA? So let us look at this diagram, right? So TCA is the moment of, so uh, uh, let's see TBA first. So TBA is moment of the area between A and B. So what is the area between A and B? Half into 24 into height of the triangle is 5 by EI. And where does so where is the centroid of this triangle? It is at 1 by 3 from this side, but we should take the moment about B. So into 2 by 3 of what is the total length? 24. So this turns out to be, so 2 gets cancelled. Uh, this is some 5, so 24, 8. So 5, so this will become 8. So 5 8s are 40. So 24 into 40. Okay. By EI. And what is TCA? So TCA you have a rectangle and a triangle. So split it up. So the point A is at so for the triangle part it is direct. So the total area is 12 into what is the height? So it's mid height. So 2.5 by EI. And where does it act? It acts at half distance into 6. Okay. And it's a positive moment, so this is also positive sign. And for the triangle, what it is? So triangle height is 2.5. So half into base is 12 meters into height is 2.5 by EI. And where does it act? It acts at 2 by 3 of 12. So again 3, this is 4, 2 gets cancelled. So 2.5 into 4 is 10. So 120. And this side we have 2.5 into 6 is 15. So 15 into 12 is 180. So here we have 300. So this is 12. I hope I'm right. 12 into 15 is 180, yes. And so this is 300 by A. And delta C, what does it say? Delta C is TBA by 2. So it is 12 into 40, which is 480. Is 300 by EI. So it is 180 by EI. So that's the right answer. So we have found delta C as 180 by EI in this case. So if you have any values for EI, you can substitute, but it's okay. It's just algebraic. So let me pause for a moment and you can ask me if there are any doubts in this or the theory section that I just covered. Other problems are very similar. We can do it very fast. So if there are any doubts, I'll be happy to answer. Is there a doubt? Can I go ahead?
Yes, sir.
Okay, thank you. Okay, let's go to the second problem. So in the case of a simply supported beam, instead of applying a concentrated load at midpoint, if the load of the same value is equally distributed all over the beam, then the maximum deflection in the first case is related to the second case by. So it is simple. What they are saying is you have a simply supported beam. In one case, you are applying a point load and you see how much it deforms. And that they call as delta 1. So let this load be P. And in the second case, you're distributing the same load in a uniform fashion. So how much is the load magnitude? It should be P by L. And then it deflects by an amount delta 2. Now what is the relationship between delta 1 and delta 2? So let us use one of the any one of the methods to find any one of the methods to find the deflections. So you can also use the double integration, but double integration is particularly useful when, as I said, for the method of joints and sections. If you want the displacements everywhere in the beam, double integration is very good. If you want the displacements at a particular point, moment area theorems will be very helpful. So let us use moment area theorem in this case. Now, before that, let us also use symmetry. So if you see the structure, if you see the deformed shape, in both cases, it will be something like this. And at these 2 points, the displacements are 0. And the deflection at any, so there's a center is a line of symmetry. The reactions are same, bending moments are the same, and the displacements are the same. So this is a line of symmetry. So if you take 2 points at the same distance from the line of symmetry, they'll have the same displacement and the slopes, same slopes, right? So at this point, about this, if you have at least in magnitude, right? So this will be a positive because of the convention. It turns signs as positive and negative. But so what you see is at this point at a distance x from the mid. So let me call some x1 on both sides. Here the slope is theta. At the corresponding here the slope will be minus theta. Or here if it is minus theta, here it will be theta. Now let us tend x1 slowly equal to 0, right? Which means we reach this point C, center. So what does this say? It means that at a distance 0, if the slope at this point is theta C, it should be equal to minus theta C. Because it's the same point and it is at the same distance from the center plane. So because of symmetry, what does this mean? This means it has to be equal to 0 because no number is equal to the no non-zero number is equal to its negative. So it should be 0. So the slope of the elastic curve at the midpoint when the beam is subjected to symmetric loading and boundary conditions is 0. So I hope you know this substructuring technique. If you have a simply supported beam or a plane of symmetry, you can always replace it as a guided roller. So you have which maintains the slope of 0, but it is free to displace. The displacement is not affected by the symmetry conditions, but the slope has to be 0. The reason is if it has a slope, then if you flip the beam, it will have a negative slope. But that is not allowed if it is symmetric. So if the slope has to be its own negative, then it has to be 0. Now our task becomes very easy. So let us just draw a tangent at the point C. How much is this? This is delta C, right? In one case it's delta 1, in the other case delta 2, but in general it's delta C. So how much is delta C? And we know the displacement of the point A and B are zeros. So how much is this? This by definition is the tangential deviation of the point A with respect to a tangent drawn at C. So because of symmetry and other conditions, we get T of A with respect to C is equal to delta C. So this is a great simplification. So we can directly go ahead and find the delta 1 and delta 2 in one step. So in the first case, what is the moment diagram? How does it look? So you should be experts in that by now because you have solved so many assignments and so if you're not clear about it, you can always find the reactions. So it will be P by 2 and P by 2. And at the center, if you take a moments about the point, the distance is L by 2. So P by 2 acting at L by 2 will be PL by 4. So in the first case, the moment is it's like this, maximum PL by 4. Now what do we need? We need T of A with respect to C. This is the point A, this is the point C, this is the point B. So in this case, it is this regions. This regions, the moment of this area about the point A. So what it is, and this is positive, remember, this is positive. So we get, yeah. So we get delta C is equal to T of A with respect to C is equal to what is the area? Half into L by 2 into height is PL by 4. And where does it act? 2/3 from this vertex, 2/3 of L by 2. So this 2 and 2 will get cancelled. So you will get, let me see, PL cube by okay, this is moment. You also have the you need to take the M by EI diagram. So this thing will be divided by EI. So there'll be EI term below. So 2 2s are 4, 4 4s are 16, 38. Sorry, 16 these are 48. PL cube by 48 EI. So delta C, that is this is delta 1. So in the case of this is delta 1. And in the other case, so when you have a distributed loading of W, the bending moment is quadratic. You know that. If you don't, if you're not clear about it, so you know what is this WL by 2. This will be WL by 2. Take a section here, and there will be moment distributed forces acting all along. So you will get the bending moment m of x as WLx by 2 minus WX squared by 2. Now if you find, so this is nothing but a parabola. So it looks like this. The maximum at the middle. So what is the maximum value? Just substitute x equal to L by 2 at this. You get W L squared by 8, which is positive. So you need to take the moment of this area about this point. So if you do that, what you get will be, so the shortcut again is use the, so the area of a parallelogram is area of a parabola between 2 points is, so if its height is WL squared by 8, if it is half, okay? This formula does not apply if you take anywhere in between. So if you have a parabola which is ending at slope 0, so in that case it is 2/3 of the rectangle enclosing it. So if a rectangle enclosing it is of this much size, so this is the rectangle enclosing it. So the area of this is, so delta 2 is half, no, not half, 2/3. 2/3 into what is the area of the rectangle? Area of the rectangle is L by 2 into height of the rectangle is WL square by 8. So this is the area. So for moment you need to take the centroidal distance. So centroid of the parabola is at 3 by 8 from the longer side and 5 by 8 from the 0 side. So this is 5 by 8. So if you have a parabola, it's helpful to remember this. You should have a parabola ending at a slope 0. In that case, the area is 2/3 of rectangle. If it is L and H, this is L, this is H. Area of 2/3 of the rectangle. And the centroid lies at a distance x bar, where x bar, as I showed, is 5 by 8. So this into 5 by 8 of L by 2. So this is delta 2. But what do we have? We have that the loads are the same. So the total load WL is equal to P. So here I can replace WL as P. So what do I get? Delta 2 as, again 2 gets cancelled. We get 8 3s are 24. 24 2s are 48. I'll get a 5 by 8. P L L L. So PLQ by 48. So what is the difference? I get delta 2. Again, PLQ by 48 EI. We already did, we found it is delta 1. So delta 2 is nothing but 5 by 8 delta 1. So that's the answer. So delta 2 is 5 by 8 delta 1. Let's go to the next question. Now let us find the value of the maximum deflection of the following beam under given loading conditions. Now, could anybody tell me which method to use? Can we use moment area method? We can use.
Yes, sir.
Yeah, you can. We can use moment area method, but there's a trick. There's a tricky situation. Why? Now you can see the loading Q of X. Q of X, which is the distributed loading, is linear. Right? It is something proportional to X. So if you integrate it, the shear force will be something proportional to X square. So that will be quadratic. So bending moment will be cubic. So the bending moment is a cubic function. So we'll have a cubic function, right? It will look something like this. Sharply increasing cubic function. And for that, we don't have any standard formula. as I said, for a parabola, we have 5 by 8 and so on, right? So anyway, we have to integrate. So there's no standard formula in this case for cubic. Yeah, we can derive, but it's not easy to remember in all for all cases in a cubic. For a cubic polynomial, the area under the curve, it's not easy to remember. So instead, let us use double integration. Okay. So if you start with the moment area theorem, you will get an answer. You have to proceed. Only thing is, while determining the area, you have to use integration. So anyway, it will correspond to using the usual double integration only. So let us go ahead. Let us find out. The bending moment. So let us make a section here at a distance x from the right end. So x is 0. So this is x equal to 0 and this is x equal to L. Taking this way, we'll see in a minute why it is easy. Why? Because we don't have to determine the reactions. We can straight away get started. So let us write down the moment. We don't need to find even the shear force. We can directly find the moment. So what it is, m of x is equal to, so consider the small beam, section of the beam, the distance x. So what is the total force that acts? It is half of, and what is the intensity? So maximum is 6 occurring over 4 meters. So the slope of this is 3 by 2. Slope of this line is 3 by 2. So maximum intensity is 3 by 2x. So what is the height? It is 3 by 2x. And what is the length? X. So this is the area, right? We're finding moment. So the total force acting on this section is this. And what is this? Where is the centroid? Centroid is 1/3 from this side. So it is into 1 by 3x. So 1 by 3 and this will go away. You get cubic moment as we expected. Positive or negative? It is negative, right? Because you assume here it is like this. If you enforce the equations of equilibrium, you'll get a hogging moment minus x cubed by 4 kilonewtons meter. And what is m by EI? So m by EI is minus x cubed by 4 EI. This is equal to d square by b. So what is dv by dx? Integrate this once. What do we get? Minus x power 4 by 16 EI plus integration constant C1. Integrated again, we get v of x as minus x power 5 by 16 fives are 80. So 80 EI plus C1x plus C2. Now what are the boundary conditions? So C1 and C2 are unknown. So what are the boundary conditions? So at the point L, both the slope and the deflection are 0. So boundary conditions are V of L is equal to dv by dx at x equal to L, both are 0. So what is dv by dx at x equal to L? Can see here, right? So dv by dx at x equal to L is this. So from that, what do you get? We get C1 minus L power 4 by 16 EI equal to 0, which means C1 is L power 4 by 16 EI. Now, substitute that C1 in this and find C2. So to find C2, let us enforce V of L equal to 0, which means minus L power 5 by 80 EI plus what is C1? L4 by 16 EI into L. So this will become L power 5 plus C2 equal to 0. So let us find C2. So this is nothing but 5 by 80 and this is 1 by 80. So we'll get 4 by 80. So we get C2 as minus L power 5, 4 L power 5 by 80, which is L power 5 by 20 EI. Now what is that we need? We need the maximum deflection. So we know that the maximum deflection occurs at the point B. So Another thing. So how do you know the maximum deflection occurs at the point B? Shear force, right? So wherever the shear force is 0, the maximum deflection occurs there. And shear force is 0 here, right? Everywhere else it will have to resist the applied force. So everywhere else it is non-zero and shear force is 0 at the point B. So the maximum, sorry. We are, sorry, that's wrong. That's not correct. So we know by physical intuition, we know that the maximum deflection has to occur at the point B because it's the free end. So if you find delta B, right? So delta B is nothing but the deflection at 0. So it is so what it is nothing but C2, right? If you substitute x equal to 0 and v of x, you get this term vanishes, you get C2. And C2 is nothing but minus L power 5 by 20 EI. Now it is given L is equal to what? L is equal to 4 meters. L equal to 4 meters. And EI is equal to, so E is some 200 GPa, I is something else. So we get E is 200 GPa. I is something into 10 power 6 mm power 4. What it is? 100 into 10 power 6. Which is nothing but 100 into 10 power 6 into 10 power minus 12 meters power 4. And this is equal to 200 into 10 power 9 Newton per meter square. So basically EI will be 200 into 10 power 9 into 100 into 10 power, so 100 is 10 power 2, 10 power 12. So 10 power 8 minus 12. So we get just 10 power minus 4 Newton meter square. And this is nothing but 200 into 2 into 10 power 5, 7. So Newton meter square. Now let us compute this value, right? And what is the numerator in? So we have already taken this 3 by 2 somewhere. So 3 by 2 is, kilonewton per meter per meter. So it's nothing but 3 into 1000 by 1000 into 1000 newtons per meter. So there's another factor that needs to be multiplied here. If we want the answers in meters, the delta B will be minus L power 5 into this factor, which is 10 power minus 3, divided by 20 into EI is 2 into 10 power 7. Newton meter square, not Newton per meter square, Newton meter square. This is also Newton meter square. So how much is this? Let us find out. L is 4 meters, right? So 4 power 5 star, or let's 10 power 3 divided by 20 star 2 star 10 power 7. Let us see, something is not correct. So what do we get? It's actually, so let us see, it is 4 power 5. Oh, wait. I think the issue is with the precision. So let me say format long. So it is 2.56 mm. This is in meter, so the answer is 2.56 mm. Which is this. So it's option B. Let's go to the next question. So find the value of the deflection at point B of the following beam. So here, what helps us is principle of superposition. Principle of superposition. So before that, for the numerical quantities, right, let me store this value EI as 2 into 10 power 7. So later when we use, it will be helpful. Now simple. So let us decompose the problem as one problem where we have the point load alone and one problem where we have the distributed load alone of intensity Q of intensity P. Length is the same L. So the total deflection of the point B is in the first problem plus the deflection in the second problem. So let us solve the point load problem. Of course, you all know the answer very well. It's a standard problem, right? You know it is PL cube by 3I, but let's get it by one of the two methods, okay? So as usual, you know the bending moment diagram is triangular. So what is the maximum moment? It is P into L. That's all. And it is negative. It's not positive, it is negative. So it is minus PL. What is the M by EI diagram? PL by EI. So what is the deflection at the point B? Now it helps. So let us sketch the elastic curve. It will be something like this. It's exaggerated. This is delta B. But if you draw a tangent at the point A, since A is a fixed support, it has to have zero slope. If you draw a tangent at the point A, it will be like, sorry. It has to be along the beam. It has to be horizontal. So this is the tangent drawn at point A. So delta B is nothing but, by definition, this is T of B with respect to A. So delta B is nothing but T of B with respect to A. And what it is? Very simple. We have the moment, so it is half. So the total force, so total area is half into minus PL by EI into length is L into where is the centroid? From this side, it is 2/3 of L. So how much it is? So as expected, 2 gets cancelled. We get minus PL cube by 3EI. That matches, correct? Then for the distributed load problem, you have again same delta B is this. So let us find out what is the bending moment diagram. The bending moment diagram, you know, it is so simply it is minus qx square by 2. So if you know very well how it comes. So it is minus qx square by 2. Let me draw it like this. And the maximum value is minus ql square by 2. Right? So what is the tangential deviation? Now you should be careful because it is not a parabola. So if this portion, so this is called parabolic spandrel. This is called a parabolic spandrel. So if you have so inside a rectangle, if you have full parabola, This is what you call parabolic spandrel, and this dotted region, this is what you call as the parabola. So for this region, it is 5 by 8, 3 by 8 and 5 by 8. For the dot, it is 5 by 8 and 3 by 8. This is where the centroid is. For this, the centroid is somewhere else. For this, the centroid is at, let me check. 1 by 4. This centroid is at 1 by 4 and 3 by 4. So if this portion covers 2/3 of the rectangle, so this area is 2/3 of rectangle, which means this area has to be 1/3 of the rectangle. So in this case, for this parabolic spandrel, how do we find delta B? Very simple. So what is again area under the M by EA diagram? Again, there's a EI here. EI. Area under the M by EA diagram is 1/3 of the rectangle into 1/3 of the rectangle is what? A rectangle is QL square by 2EI into L. And where does this act? So it is 1 by 4 from this side and 3 by 4 from this side into 3 by 4L. So 3 gets cancelled. You get QL power 4 by 8EI. This is the displacement. Now let's find these magnitudes in actual correct magnitudes. So what is P? P is 10. And this is also negative, right? This is also negative. So P is 10 kilonewtons. So it's 10 into 10 power 3 into L cube. How much is L? L is 4 meters. So into 4 cube by 3 EI, let it be EI. Okay. And here, what is the thing? Q is how much? Q is 4. It is 4 kilonewtons per meter. So when you convert it to newtons per meter, it is into 1000 by 1000. Sorry, wait. Kilonewtons per meter. When you convert it to newtons per meter, it is 4 into 10 power 3. L power 4 by 8 EI. Now, how much is this? So what we'll see, what is 10 into 10 cube into 4 cube by 3. That is some 2.133. So system 2.133 into 10 power minus 5 meters. And this one, it is simple, right? So 4, this is half. 4 power 4 is 256. So this is 128. 128 into 10 power, sorry, 10 power, not minus 5, 10 power 5. And here it is 128 into 10. So let us just do it. 4 power 5 by 8 star 10 power 3. So it is 1.28 into 10 power. So this one is 1.28 into 10 power 5. Hope I'm right. 128,000. So what is the total? So total displacement by EI. There's a by EI everywhere. So this is by EI, not meters. By EI, meters. So total displacement is 1.28 plus 2.133, which is 2.133 plus 1.28 into 10 power 5 by EI, by principle of superposition. Let us find what it is. So 0.13333 plus 1.28 star 10 power 5 by EI. It turns out to be 17.067 mm. So that is this. Let's go to the next problem. Find the deflection at the point C of the following beam. It's a very, very simple problem. You are asked at an internal point. So directly apply the moment area theorems. It's a very simple problem, as I said. And what is the tangents? Tangent at A has zero slope, as in the previous problem. For all cantilever beams, this is an advantage, which means the deflection of point C is the tangential deviation of the point C with respect to the tangent drawn at A. So again, this is the deflected shape. This will be delta C, and that's also equal to the tangential deviation TC with respect to A. What's the bending moment of this beam? Very, very simple. You take a section anywhere, the moment is 5 kilonewton meters negative. So M by EI is minus 5 kilonewton meter by EI. Now, where is the point C? Point C is here at 3 meters and 1 meter. Now, which area we should consider? This area. So what is delta C? For the area? Area is minus 5 by EI into 1. And where's the centroid? It acts at half. So it is nothing but 2.5 by EI. Note that EI in this case, in the last problem it was 100. In this case it is 200. So what do we get? 2.5. We get 2.5 kilonewton meter. So if you convert it to Newton meter, we get 2.5 into 10 power 3 divided by EI. So EI, you should be careful. In this case, it is 2 times the last. So it is 200 GPa. So 200 E9 star. I is what? 200 E6 star 1E minus 12. So it is 6.25 into 10 power minus 5 meters, which is nothing but 0. So it is 6.25 into 10 power minus 5 meters, which is 0.0625. And we have a minus sign, right? We have a minus sign here. So minus sign means it's downwards. So let's proceed to the next question. Some water. Now again, this is again a problem where you can apply superposition. Okay, so we have two loads. Split it up into two problems. So first superposition. So you have one problem where you have only the end load. Plus the next problem where you have only the midspan load. Now what is asked? We are asked the deflection at the point C. So this is the point C, this is the point A, this is the point B, and this is the point D. Now let us draw the bending moments. So you must be very familiar now. So let's take problem A. Let's call this problem 1 and let's call this problem 2. So for problem 1, can we quickly get the before that? So yes, as I said, for always, let us draw the deflected shift. Let us guess the deflected shift. We guess it should be something like this. Because we have a load acting here and we have a load acting here. So the deflected shape must look something like this. And we are asked the deflection of this point, which is this. So let me draw it without the loads once. There's no symmetry. We are asked the deflection of this point, which is delta C. And yeah, that's what this is point B. Now, as we did for the first problem, right? Let us take this point as A, D, B. Let us draw a tangent at A. It's inclined at theta A. And what is this? This is TD with respect to A. What is this? This is TC with respect to A. Now, what do we know about TD with respect to A? Because the point D does not deflect, right? The point D is fixed. It cannot deflect. So we can directly compute TD with respect to A. Again, using similar triangles. So if you see, we get TC with respect to A plus delta C by AC is equal to TD with respect to A by AD. Because the angle theta A, what is this equal to? This is equal to tan theta A, of course. So again, what do we get? We get delta C is equal to AC by AD TD with respect to A minus TC with respect to A. And what is AC by AD? This case it's half. So it is. So delta C is half of TD with respect to A minus TC with respect to A. Same as the first problem. Now let's consider the two sub problems. So for problem 1, where only this end moment is acting, what do we know? So for problem 1, let's quickly get the bending moment diagram. What is the moment? What's the moment at the point B? Right? There's a load P acting here. So the moment here will be, and it is hogging. So let me draw it on the other side. So this is linear, right? So this will be minus P into, let's take the span as L, this distance as L. And in this problem, there is nothing else. Here it is a zero moment. So just connect it by a straight line. There's no other discontinuity in the, sorry, take this as minus PL and this is 0. Now the point C is here. Now what are all the quantities that we need? We need TD with respect to A and we need TC with respect to A. So what are the areas that are required? This one and the full one, this one. See this one. Very simple. What is TD with respect to A? It is, and this is L and this is L. So what is TD with respect to A? Area is half. Height is PL by EI. Distance is L, not L, 2L. And where does it act? TD with respect to A, moment should be taken about the point D. So from here it is 1/3 of 2L. So how much is this? 2 gets cancels. We get TD with respect to AS 2 2PLQ by 3EI. And what is TC with respect to A? Simple, same. Half. The intensity is PL by 2EA because it is halfway. And what is the length? L. And where does it act? TC with respect to A, right? So the smaller triangle. So where does it act? It acts at L by 3. So it acts at L by 3. So this is nothing but P LQ by 3 4 so 12. 12 EI. Now what is delta C from problem 1? It is half of this one. So PL cube by 3 EI minus PL cube by 12 EI. So 1 by 3 minus 1 by 12 is 4 by 12 minus 1 by 12, which is 3 by 12, which is PL cube by 4 EI from the first problem. Now let us look at the second problem, which is even simpler. So second problem. So the load P is acting at the midspan. And this is just free of anything. So if you take the support reactions, right? There are two supports equidistant. Can quickly find out this will be P by 2. This will be P by 2. So the maximum moment will be at the middle, which is positive. One more thing. So this is negative, right? This is negative. So we missed this minus sign here. There's a minus, minus, minus everywhere. Minus, minus, minus. And here it is positive because it is sagging moment. And of magnitude, PL by 2 acting at L by 2. So PL by P by 2 acting at L by 2. So PL by 4. Now this is the point C. This is the point D. This is the point A. So what is TD with respect to A? Very simple. So what is the total area? It is half into 2L into height is PL by 4 into where does it act? So it is a symmetric isosceles triangle. So it acts at C. It acts at exactly at the middle. So it so the distance is L. So this is PL cube by 4EA, and that's an EA. Right? What is TC with respect to E?
Sir, one doubt,
So
sir.
yes.
So the triangle that is PL by 4, instead of PL by 4, I think it is PL by 2.
Oh yes, yes.
Bending
It is
moment,
P into
because
2L by yeah. Thank you for pointing out. It's a mistake. P into 2L by 4, so it has to be PL by 2. Correct.
yes.
So this will be PL by 2EA. Yeah, thank you for pointing it out. So and then yeah, so TC with respect to A is what? So half into distance is L. So this is TC with respect to A. Distance is L. Height is PL by 2 EI. Into this, where does this act? So this acts at L by 3 from here. So into L by 3. So this is nothing but P L cube by 12 EA. I didn't make any mistake. Yes. So now again the same thing. So delta C is half TD by A minus TC by A, which is PL cube by 4 EI minus PL cube by 12 EI. Just a minute. Did I make any? Yeah, this is fine. So this is 3 by 2. Sorry, this is 3 PL cube by 12 EI minus 1. So it is 2. So in this case, it is nothing but PL cube by 6 EI. This is positive. So this is the this is what is coming from second part. So what is the total delta C? It is delta C coming from the first part plus delta C coming from the second part. So that is from the first part we got minus PL cube by 4EI plus PL cube by 6EI. We get minus PL cube by 4EI plus PL cube by 6EI, which is minus so this is LCM is 12, so this is 3 by 12 and 2 by 12, so minus 3, so minus PL cube by 12EI. So since it is negative, no wait, this can't be negative. Let me check once. So TC with respect to A is fine, it can be negative. If it's negative, it means our assumed direction is wrong. So we assume delta C downwards as downwards. So if we are getting negative, it means our assumed direction is wrong and it is upwards. So let us see what the value is. P is 30 kilonewtons. So in our case, P is 30,000.
Also.
L is yes. Let's see what it is. P is 30,000. L is 2 meters by 12, right? 12 into EI. EI is 2 star 10 power. I think we need to see something here. Two cube is 8. So by 12 into 2 into 10 power 7. Yeah, so PL cube, right? So 2 cube is 8. So the answer is 1 mm. So we have negative. So this is minus 1 mm. But remember, we assume delta C as downwards. If we are getting negative, it means it is upwards. So let's check. So it should be 1 mm upwards. Let me check the answer. Yeah, 1 mm upwards. So this is the answer. Problem 7. Again, this is a very simple problem. Find the value of A for which the deflection at the end will be equal to the deflection at the center. Now, again, it is symmetric. So don't use superposition. That is not that you have to solve two problems. Instead, just make it as symmetric. Okay. So if it is symmetric, you know that at the midspan, as we already saw, at the midspan, slope is equal to 0. It has to be 0. If it is not 0, then it will not be symmetric. The deflection will not be symmetric. So how will it deflect? It will deflect something like this. Maximum will occur here. So if you draw a tangent here, it will be flat because the slope is 0. Tan theta is 0. How much is this? This is TB with respect to A. No, not A. So this is TB with respect to, say, call this point as C. and call this endpoint as D. And this one is TD with respect to A. Now, how much is, so we know that the point C. So point B is fixed, which means TB with respect to A. So what is TB with respect to A? Basically, it is delta C. Why? This is delta C. So this is an assumed pattern. This is correct pattern. So this is assumed. So I'm assuming delta C upwards is positive, and TB with respect to A, it will have the usual sign. And what is delta D now? So delta D is nothing but TD with respect to A minus TB with respect to A. Sorry, not A. This is C, right? Make it all C. So total is TD with respect to C. But only this much is deflection. So TD with respect to C minus TB with respect to C. So quickly, so what is the bending moment? I'll draw right below this. You have a support here, and you have a support here. And what else? And it is symmetric. So here, if you have P, this will also be P. And this, if you have P, this will also be P. So at any other point, right? Right, if you take moment about any point here, the net force acting in this section is 0. So the shear force is 0, which means the slope is 0. So the bending, so it's nothing but a 4-point bending test. What you get in a 4-point bending test, so the moment will be something like, my bending moment will be something like this. So this distance, let us take it as A. So they are taking it as A. So the bending moment will be something like this. This is the point C. This is the point B. This is the point D. Now, what is the condition that they are, and what is the magnitude, right? Magnitude is P into A. That's all, simple. Positive or negative? Negative. Because it is about this point, it creates a hogging moment. Now, and we need, of course, the PA by EA diagram. What are they asking? They're asking that the deflection at the center should be equal to the deflection at the end. And so what does this mean? It means delta D is equal to delta C. And what is delta D? TD with respect to C minus TB with respect to C. That should be equal to delta C, which is TB with respect to C. C. So what is the condition? TD with respect to C should be 2 times TB with respect to C. What does it mean? So you take, so what is TD with respect to C? Moment of the area between these about the point D, that should be twice the moment of the area between B and C about the point D. So let us quickly find out what is TD with respect to C. So TD with respect to C is, let's split it up into one rectangle and a triangle. So for the rectangle, area is PA by EI, acting over how much length is this? This is L minus 2A. So it is L by 2 minus A. L by 2 minus A. Where does it act? It acts at L by 2 minus A, the midpoint, right? So it acts at L by 2 minus A by 2. L by 2 minus A by 2 plus this distance, which is A. This is due to the rectangle and it's negative, and the part due to the triangle, which is minus PA by EI, half of PA by EI acting through A. And what is the moment lever arm? It is 2/3 of A. So this is TD with respect to C. Let's find out what this is. It is let's take P by A commonly out. It will be minus P by EI. If we take it commonly out, we get, in fact, we can also take an A out. We get L by 2 minus A, the whole square. There's a half plus L by 2 minus A multiplied by A plus here we have A square. So this is a 2 and 2 is cancelled. We get A square by 3 A square by 3. So let's just expand. It is minus PA by EI into what does this become? L square by 8 minus 2AL in AL by 2. So minus AL by 2 plus A square by 2 plus AL by 2 minus A square plus A square by 3. So this is minus PA by EI. L square by 8, AL by 2 plus AL by 2 minus AL by 2 plus AL by 2 will get cancelled. And then we get plus A square by 2 plus A square by 3, which is 5 by 6 A square. Minus A square is minus A square by 6. So this is what is TD with respect to C. TB with respect to C is even more simple. So TB with respect to C is nothing but half, not half. So it is P A by EI acting at L by 2 minus A. Sorry, P A by A base is L by 2 minus A acting at half of L by 2 minus A. So it's nothing but, and there's a minus PA by EI into L by 2 minus A the whole square. So let's go down. So TB with respect to C is minus PA by EI into L by 2 minus A the whole square. Now what is the condition? TD with respect to C is 2 times TB with respect to C. So if we solve it, we get TB with respect to C, 2 times that is TD with respect to C, which means minus PA by EI, L square by 8 minus A square by 6 is equal to 2 times minus PA by EI, L by 2. So this is nothing but L square by 4 minus LA plus A square. PA by EI will get cancelled. PA by A will get cancelled. We get L square by 8 minus A square by 6. Just a minute. TD with respect to C is negative. So delta D is, we need to compare only the magnitudes, right? So yeah, it's correct. So we get L square by 8 minus A square by 6 is equal to L square by 2 minus 2LA plus 2A square. So just rearrange, we get L square by 2 minus, so 4 by 8 minus 1 by 8, which is 3 by 8. So I get 3 by 8 L square minus 2LA plus 2 plus 1 by 6. So that is 1 by 6. So 13 by 6 is equal to 0. Now we have to solve this quadratic equation. What is the solution? Let us solve it. We get, so we need A by L, right? So let's normalize it. We get, or let's make it a square minus 12 by 13. So this is a by L the whole square. Let us take, right? Let's divide root by L square and divide it by 13 by 6. So we get 12 by 13 a by L plus we have 3 by 8 L square by L square will go away into divided by 13 by 6. So it is into 6 by 13 into 6 by 13 equal to 0. So let us solve this. So if we solve this, so just solve. Let me. Let me check. So we are having B fixed. So this is fine. So 2 TDC, this is TBC. So this is 2. And TB with respect to C is PA by EI acting through L, what this into half. Okay. So this, yeah, there's a half missing here. So TB with respect to C, there's a half missing here. That's an issue. So there's, so here this 2 and 2 will get cancelled. We wouldn't have, so this remains L square by 4 and this remains LA and this will remain A square. This is, sorry for this confusion, we'll get so the correct, so we get L square by 8 minus A square by 6 is equal to L square by 4 minus LA plus A square. So the correct equation is L square by 4 minus LA plus 7 by 6 A square is equal to 0. So if you will get A by L the whole square minus 6 by 7 A by L multiply throughout by 6 by 7 plus 6 by 7. So 6 by 28 is equal to 0. So the sorry for the typo. There it is. share it again. So it is so a square minus it is 6 by 7, not 12 by 13. And here it is 6 by 28. Wait. So we need to see that delta C is so the minus sign, right? It should be there's a sign mistake here. So delta C is TB with respect to C. The point, but B lies below the tangent at C. So there's a minus here. So delta C is minus of TB with respect to C. So this minus sign will be taken off. TB with respect to C, this minus sign will disappear. And TD with respect to C also. And delta D is mod of this minus mod of this. So TD with respect to C is this. So this one minus delta C is equal to delta C. So that is fine. Square by 4. Something is not correct here. Well, sorry for the issue. Let me clarify this in the next session. But when I did it last time, it was all right, but I'm not able to correct the issue here. So let me go on to the next because of the lack of time. Okay, so again, this is a simple problem. We need to find this is a cantilever beam. So the deflected profile is something like this. This is the point C. This is the point B. And the tangent here is horizontal. So they're asking the slope at the point C. So we know now use the first moment area theorem. And this is horizontal. So the slope of point A is 0 by boundary conditions. Theta C is nothing but theta C with respect to A. So what is the bending moment? Let's draw the bending moment. At the point C, if we look at the total moment, so up to the point C, it will be quadratic because it's and what is the total value? It is 6 square, 6 into 2 square by 2, minus 6 into 2 square by 2. It is minus 12 kilonewton meters. at this point. Beyond this, what is the total force? So the total force is 6 into 2, 12. 12 newtons acting at 1 meter from here. So it's totally 3 meters away from here. So 3 into 12, what is the max? So 3 into 12 is 36. So beyond this, it is linear. Up to this point, it is quadratic. Beyond that point, it is linear. So I hope you get why it is so. This total height is minus 36 kilonewton meters. And what is required? We need theta c with respect to A, which is this area of a trapezium. So you know very well what is the area of a trapezium? Half B1 plus B2 minus 12 plus minus 36 into height. What is the height? 2 meters by EI. So what is EI? EI is our 2 into 10 power 7. So how much is this? And this is in kilonewtons meter. So I need to convert to you need to convert it to Newton meter. So we get 12 plus 36 is 48. So 48 by 2, it is 2.4. 48 by 2 is 24 into 10 power 6 by 10 power 7. So it is, let us check. It is, so this is in kilonewtons per meter. This is in kilonewtons meter. So it's not 10 power 6, 10 power 3, right? So kilonewtons to newtons is 10 power 3. So 10 power 3 by 24 into 10 power 3 by 10 power 7, it is 24 into 10 power minus 4. So it is 2.4 into 10 power minus 3 radians. This is the answer. Let's also check it. Yeah, it's the correct answer. Now let's go to the second last problem. What is the deflection? What is the deflection at? Again, as usual. So what is the value of the deflection at point B of the given B? So let's do it. So it is, the deflected shape is something like this. Load is acting only here. We are asked to find the deflection of the point B, which is this much. Now I can tell you one more thing. So if you consider only the, if you just consider the span AC, and at the point C there is no, so the span CB is not carrying any load. So due to the span there is no reaction or moment coming at the point C. So the entire reaction at point A and C comes only from this loaded span. So if you see the free body diagram, it will look something like this. It will be 2.5. Sorry, not 5 into 2, right? So it will be 5 and 5 kilonewtons. And you have the distributed load here. So if you take the bending moment diagram, it will be something like this. So how much is this? 5 into 2 square by 2. Sorry, 5 into 2 square by 8. So you have 5, and so 5 acting at 1. So we get 5 acting at 1 minus what is the effect from this? So we get, it is 5 into 1 acting at half. So it is nothing but 5 by 2, which is 2.5 kilonewtons meter. The maximum is 2.5 kilonewtons meter. Now, given this, the maximum deflection, right? Okay, let's do it in the usual manner. So this is 2.5 kilonewtons meter and by EI as usual. As I said, you need to select a point about which you need to find that tangential deviation. So here, the full, so if this is a tangent at A, we know the point C is fixed, and this is TC with respect to A, and the full thing is TB with respect to A. Now what is delta B? And we don't know what this is. Let us call this as some quantity y. So what do we know? Y plus delta B is equal to TB with respect to A. But using similar triangles, you can say that y is also equal to 2TC with respect to A. Why? Because this is 2 meters, this is 4 meters. So this length is twice this length. So y should be equal to 2TC with respect to A. So what do we get? Delta B is equal to TB with respect to A minus, in this case, assuming that our signs are defined this way, so delta B is equal to TB with respect to A minus 2TC with respect to A minus y, which is 2TC with respect to. So what is TB with respect to A? So this is the point, and this is a full parabola. So the total area is, so TB with respect to A is total area, 2/3 of 2 into, what is the height of the parabola? 2.5 by EI. And where does it act? It acts at mid of this. So it is into 3. So TB with respect to A, so 3 and 3 gets cancelled. 4 into 2.5 is 10 by EI. And what is TC with respect to A? That is also simple. So with respect to the point A, this is a full parabola, the same area, 2/3 of 2 to 2.5 by EI. But what is the lever arm? It's not 3, it is 1. So it is 10 by 3A. Simple. Now, what is that they are asking? Where they are asking delta B, which is TB with respect to A. So 10 minus 2TC with respect to A, minus 2 by 3 into 10, the entire thing by EI. So it's nothing but 1 by 3 into 10 by EI. Let me check. So this is 5 L square, which is this is fine. Okay, here the I is different. I is 100 into 10 power 6. So here it is 1 by 3 into 10 by EI is 1.0 into 10 power 7. So what it is? So 10 power 6, 1 by 3 into 10 power 6. So it is, and this is in kilonewtons. So convert it to newtons. So this is in kilonewtons. So convert it to newtons. So I'll get another 10 power 3. So it is nothing but 0.1 by, sorry, it is 10. So it is 10 by 3 is 3.3 into 10 power minus 4 meters, which is 0.333 mm. So it is option A. Let's check. Yeah, it's correct. So the last problem for today. It's a slightly involved problem. Let's do it. So here we don't have any symmetry. Here it is statically determinate structure, although it looks like a prop, it's not indeterminate, it is statically determinate structure. We don't have any symmetry, so we have to solve the full problem. So let's do it. It's not difficult. What are the so this, let us start with, as usual, we'll start with guessing the elastic curve, okay? Or rather, since we have A, it's not an issue. So we just need, so what is asked? We are asked the slope at the point C. But we know that the point at A, so we know that this is what is asked. We know theta A is equal to 0 because it is fixed cantilever. So theta C with respect to A is nothing but theta c minus theta a is theta c. So it's enough to find theta c with respect to a. Now to get theta c with respect to a, what we need the moment bending moment diagram. Now how to get the bending moment diagram? Let us solve it. Okay. So this is let us divide the spans. So we have free body diagram. A, here what is acting? Only a vertical force. It cannot support a moment. Call it dy. So internally it should be. So here we have downwards first dy. We have cy acting here. Here we have 20 kilonewtons. Let us take moments about the point C. Okay, so let's take moments about the point C. What do we get? We'll get 20 minus 20 acting at 2 plus dy acting at 2 is equal to 0, which means dy is equal to 20 kilonewtons. Acts downwards, so here it acts upwards. So the moment at A, right? Moment at A is dy into 2, which is positive. So it is a sagging moment. It is sagging moment 40 kilonewton meter. So it is simple. Now if we sketch the bending moment diagram, it is very simple. Note that we have point A, we have a hinge, we have an intermediate support. So at this support, due to the load, we'll have a negative moment of minus 40. Here we'll have minus 40, 20, minus 20 acting at 2. But this is an internal hinge, so it has to become 0. So here it is 0. And again, here it is positive. So since the shear force is continuous, here it is positive. So here it is 40 kilonewton meter. Here it is minus 40 kilonewtons meter. Now what is asked? We need theta c with respect to A. So theta c with respect to A is let us see. Looks (22). We take moments about the point C. So let us see if it is in equilibrium. So the beam is like this. So here it is 20. Here there's an internal hinge. This is 40. And this is 20. And so in this span, the shear force diagram is we take positive 20. Here also it is positive 20. And then here it is negative 20. So 40 acts here. Looks like it is. Okay, I think the issue is this. Since there is a internal hinge, the slope is not continuous at the point D. So the slope to the left of the point is different from the right of the point. So no problem. Only thing is this is not valid. So theta c with respect to A is not valid because we cannot determine what is the we cannot determine the slope. So until this point, so at the point C, if you see, the deflected shape will be something like this. it has an upward force. It will be something like this. And at this point, the slope is no longer continuous. It cannot be. So beyond this, it will be some it will have some other slope. So it will be something like this. Something like this. So since the slope is discontinuous here, we cannot find its derivatives, which are the shear force and bending moment. It is 0. So let us do it from this set. Okay. So let us find the displacement of the point. And from that point, let us try to find out. So what is the displacement of the point D? Now, given this, this is point A, D, C and B. C and B. So displacement of point D is nothing but TC with TD with respect to A. And that is nothing but half into 40 into 2 into 2 by 3 into 2. So that turns out to be some 40, 160 by 3 EI for a displacement of the point D. Now let us see the span dB. Okay, so the span dB looks the displacement, the deflected shape of the span dB looks something like this. So it is like it looks something like this. We have this, and this is going down. Here we know the displacement is 160 by 3 EI. Now let us find the slope here. Okay, so let us find the slope here, just theta c. Theta c with respect. So let us. So for this span, the displacement is fixed. So from and here the slope is unknown. The change in slope theta c with respect to d is this area. Okay, this area is nothing but half into 40 into 2, which is again 40 by EI. And then let me check. So so this area is 40 by EI. Okay, so suppose this is the deflective shape. Suppose this is the deflected shape. We are asked to find the slope here. Let us find theta c. So this is theta c. So we found theta c with respect to b. Theta c with respect to d. That is the slope with respect to d as. So theta c minus theta d is 40 by EI. And then theta d with respect to A is the same thing. So let me check. Theta d with respect to A is the same. So this is minus 40 by EI. Theta c with respect to d is minus 40 by EI. Theta d minus theta A. So this is theta d minus theta I, that is plus 40 by EI. But the slopes are not continuous. Okay, so the left side slope, call it as theta c minus theta d. This is positive on the right hand side, and this is on the left hand side. The slopes are not continuous, so we can't say that. But what you can say is theta d. So the need here is to determine theta d. So theta d minus is well known because theta a is 0. So theta d is nothing but plus 40 by a. So theta c. And what else we know? We know that the displacement of the point D is, we know the displacement of the point D as, where is it? Uh, 160 by EI, 160 by 3 EI. That means the tangent okay. So it is nothing but T. If you draw a tangent at the point C, so TD with respect to C minus TD with respect to so at the point C, if you draw, so where is the, so here suppose we draw a tangent. This one is TC with respect TD with respect to C. And this one is delta D. And what is the total? It is theta C times this total length. And what is the total length? 2. So it is simple. Okay, so we are having so there, let me draw it clearly again. So the deflected curve is something like this. This is the point D. This is the point C, which is supported. And we have some, if you draw a tangent at the point C, this is TD with respect to C. Okay, so the sign conventions are not, so the angle, this angle is theta C. And this is delta D. This is the curve, which is, sorry, let me do it. So this, so here it has to go down, something like this. So here it is hogging and it reaches a point of inflection. So, and then it becomes sagging. So this is the deflected shape. So when, let me exaggerate it. This is how it looks. This is the point C. You take a tangent here. This is TD with respect to C. This is delta C. Delta D. But this tangent makes an angle theta C here. So the total is L into theta C. So we need to find theta C, right? So theta C is nothing but TD with respect to C. Okay, so TD with respect to C, in this case, it will be negative, but we need to take the modulus because it's so since it is lying below the tangent, it will be negative. So take the modulus plus delta D by L. So this is what we need to do. What is TD with respect to C? We just found out. Oh no, we didn't find out. Let's find it out. So TD with respect to C is half into what is the length? 2 meters. So half into 2 into height is 40. Actually minus 40, but anyway we are taking the model minus 40 into the distance is 2 by 3 from taking moments about D 2 by 3 from this modulus plus delta D. Well, delta D we got 160 by 3 EI. That's a 40 by EI by L. L is how much is L? 2 meters. So this is nothing but so half goes away. So again 40, 160, 160 by 3 EI, 160 by 3 EI. So we get 160 by 3 EI as theta C. Is it correct? Yeah, 160 by 3. Yeah, that is correct. And then so this problem, I'll go through it once again, and then I'll provide a clarification in the same YouTube series. Something went wrong here. I need more time to look into it. I don't know what mistake I did. I'll go through it and clarify it in the next session. If there are any doubts, you can ask me. Any doubts? Okay, it seems like there are no doubts except for this question, right? I'll clarify it. I'll add it in the beginning of the next session. Or I'll add it to this and then upload on YouTube so that you can watch it on YouTube by the end. So if there are no doubts, I can end the session. Shall I?
Yes.
Okay. Thank you. Thank you for staying for the extra time. Thank you for staying back. I'm stopping the recording now.